Hello everyone, welcome to our tutorial, Multimodal Data Query Languages and Processing Paradigm. I'm Chao Zhang, a doctoral student at the Department of Computer Science, University of Helsinki, Finland. This tutorial will be given by Qinsong Guo, Shuxun Zhang, and me. We come from a research team at the Department of Computer Science, University of Helsinki. The main research topic of our group focuses on the database theory and algorithm, especially on multimodal databases. If you're interested in our research, please access our website for the more detail. In this tutorial, I will first give an introduction to multimodal data query languages. Then Shuxun will introduce the SQL-based multimodal query extensions. Then Qinsong will introduce other extensions, including the document-based and graph-based multimodal query extensions and the native multimodal query languages. After that, I will give a demonstration of two multimodal query languages. And finally, we discuss some open challenges and the future directions. We often use 4 V's to describe the challenge of big data, namely volume, variety, velocity, and veracity. In this tutorial, we will focus on the variety. That means data come from different sources and naturally with different formats, such as the hierarchical data, including the XML, JSON, and the graph data, such as the RDF and property graphs, and the tabular data, such as the CSV. Consider a use case called customer 360-degree view, where a customer can own data in various applications, including the social media, gaming, entertainment, banking, finance, historical data, and the online purchase data. This shows that one application will have multimodal data. For instance, the relation data come from the customer databases, and the graph data comes from the social networks, and the hierarchical data come from the catalog of products, and the text data from the customer review. So e-commerce example will include multimodal data. The concept of multimodal database is to utilize one unified database for multimodal data. And this approach reduces integration, migration, development, maintenance, and operational issues. Therefore, a multimodal database is designed to support multiple data models against a single integrated backend. And so the document, graph, relational, and key value models are examples of data models that may be supported by a multimodal database. So a number of multimodal databases have been emerged, and they play more and more important roles in data management. To name a few, the Oracle 12c, the ArrangoDB, and the OrangeDB, etc. Based on the Gartner report for Operational Database 2016, by 2017, all leading operational DBMS will offer multiple data models, relational and NoSQL in a single DBMS platform. This is a true prediction. So in the latest DB-Engine rankings, there are 8 multimodal databases in top 10 and 77 multimodal databases among the 334 databases in total. So 2 examples of multimodal databases are ArrangoDB and OrangeDB. ArrangoDB is designed as a native multimodal database, supporting key value, document, and graph models. Suppose we have a nose graph in a social network, and a customer table with credit limit information, and two key value pairs of mapping between the customer ID and the order IDs, and a transaction order in JSON format. So these data have relationships. For example, a graph vertex join is related to a relational row and a key value pair, and a key value pair here is also related to a JSON order. Consider a query that returns all products which are ordered by a friend or a customer whose credit limit is over 3,000. So by using a declarative query language called AQL in MongoDB, we can compose a corresponding multimodal query in a single statement. So here, this data will be accessed by AQL simultaneously and return unwanted results. OrangeDB is another multimodal database supporting the graph, document, key value, and object model. It supports the schemaless, schema full, and schema mix models. For the same query, OrangeDB can also specify a SQL-like path-oriented query to return the wanted results. So in this tutorial, we classify the multimodal query languages into 4 categories. The SQL extension, such as the SQL++, in Asterisk DB, and the PL SQL in Oracle, and the document extensions such as the MongoDB API by MongoDB, and the XQuery by MarkLogic, and the graph extension examples are the XSQL, the Cipher SQL by Agents Graph, and the native multimodal query language we just mentioned, the AQL by MongoDB and the OrangeDB SQL. These are the references for the introduction, and in the next, I will pass the stage to Shuxun. Thanks.
Hello, everyone. Thanks for Chao's great introduction. I am Shuxun Zhang, a doctoral student at the Department of Computer Science, University of Helsinki, Finland. The second section will be presented by me. Chao will come back in the demonstration section. Let's get started. In the following, I will introduce the most common and possibly the most important extension in multimodal query languages. They are extended from SQL, the most important database language in history and now, even in the future. To be fair, due to the great success of the relational data model and SQL, it is difficult for database query language to completely get rid of the influence of SQL. And for many ordinary users, the learning curve of a SQL-based language will be more smooth. Therefore, it is easier to get the favor of users. You can almost find all kinds of multimodal query languages extended by SQL that supports a relational data model and another data model. As I only have 30 minutes to introduce this to you, I will first briefly introduce the core characteristics of SQL and explain why we call one database query language as a SQL-based extension and why we need them. Then, 2 main SQL-based extension directions will be introduced, which are extension to document store and extension to graph store. Finally, some interesting other extensions will be briefly introduced. Let's get started from the first section. SQL is based on relational algebra and tuple relation calculus, including four kinds of database query language, namely data definition language and data manipulation language, data control language, and transaction control language. The functions of the SQL include data insertion, query, update, and deletion, database schema creation and modification, data access control, and so on. Classical select from where clauses is the most recognizable feature of SQL. So why there are many in relational extension databases and SQL extension query languages? At first, complex application scenarios continue to grow. These applications keep generating and using data of many different data models. The traditional relational databases cannot meet this realistic demand gradually. Then the advantages of relational databases are as well known as its disadvantages. The rigorous mathematical theory foundation makes its data structure simple and clear, and the user can understand or use it easily. At the same time, it has higher data independency and better security and confidentiality. Although the relational data model is convenient for querying and processing, it is inefficient and difficult to optimize. Therefore, the need to constrictly construct a part of the database and make the rest part of database full of flexibility makes the relational-based multimodal databases and SQL-based query language flourishing. Now we enter the second part of this section, SQL-based extensions to document store. In this tutorial, the mentioned document data basically refers to XML data and JSON data. Although most databases and query languages adopt the same storage and processing schema for them, this is not always the case. MySQL, for example, has some slightly differences due to the limitation of time of the tutorial. Such differences are usually not explained in detail in the following narratives. As shown on this page, the way how SQL-based document data model extensions can be roughly divided into three extension methods. First, query language could use existing in basic data types such as text, varchar, and varchar. Second, it is a better idea to add one or some basic document object data types. We can find at present a large number of SQL-based query languages adopt this method to support document data models. Finally, there has an innovative idea to directly manipulate and processing document data as nested relational data. For each extension approach, I have listed some database query languages and databases using this language. I must emphasize that although different databases may use the same database language, they often have some slightly differences. Support for some functions may have been increased or decreased. This is due to the demand of database market and the developmental conception of different database developers. For database query language using existing basic data types, transactor SQL is the typically representative. Its users are some databases owned by Microsoft, such as Microsoft SQL Server, Microsoft Azure SQL database. I will take SQL SQL Server 2016 as an example to explain how Transactor SQL realizes the basic operations on documented data. In the following description of the operations of a query language, I will mainly introduce data definition language and data manipulation language, specifically including how to define, modify, and query data. Sometimes index is also included. Let's start from insert and modify operations. Here, insert operation is consistency with modify. Now, when the object of modify operation does not exist, insert one directly. JSON modify is a function that modifies the attribute value in JSON string and return the updated JSON string. If the modify operation modifies an attribute to none, it is delete operation. We can see the red is syntax of the transactor SQL. Here, expression is usually the name of the variable or column that contains JSON data. Path is a JSON path expression that specifies the attribute to modify. As for query, transactor SQL provides two basic query functions, JSON value and JSON query. The syntax is in red. The main differences between them is that JSON value returns the scalar values, while JSON query returns areas or objects. In addition, there is a isJSON function to determine whether the string contains valid JSON data. And for JSON, make sure to output query results into JSON format in different ways. Please see a specific example. Suppose many people are applying for vaccination in Finland. The hospital needs to know which languages are used by those who speak foreign languages in order to provide appropriate services. A possible query and corresponding output is shown in the page. First, it is the query. Select a person ID, full name, JSON query, and customer fields, other language as languages, form, application, dot people. The possible output is shown here. We can see two results is output. First is the person ID 10010. His name is Shu Xunzhang, and the other language he used is Wu Chinese. The another is is 10086. The full name of him is Qin Guo. The other language he used is Cantonese. Next, I will introduce the second extension method to support document data, adding one or several basic document object data types. At first, we use the case of MyCircle. Actually, not only MyCircle. TI-DB is also adopts the same method used in MyCircle, although just limitation subset. The JSON definition in MyCircle is very easy. Just add a JSON directly after the column name. It is no different from other types of data. Or you could use cast functions to cast the values of other types to JSON type. The syntax is in red here. As for insert and modify, we could use two ways to insert data. First, directly insert a string in JSON format in the form of an object or an array. And syntax is in red. Insert into table and the value. Or we could use JSON object and JSON area functions to generate a JSON dash. As for modify, when update the whole JSON variables, the operation is similar to insert. Besides that, we have a set of functions to implement the modify operations. Then we talk about query. When querying the whole JSON column, it is basically no different from querying other types of data. That is basically no difference from standard SQL. When query the data in JSON, the syntax is in the form of column to pass, where the representation of object type pass is in red here, and the representation of array types is in red here. Similarly, let's see a specific example we previously has used. At first, we insert my application data into the apply table. Then we check what other language is used by me. Please see here in blue. The syntax is insert into apply table name for then is the column name, full name, age, language, with the values 属勋章 the age, and JSON text. It contains two key value sets. Main language is English, and the other language is Wu Chinese. Then we check the detailed information. We select ID, full name, and language to other language from apply. The output is showing in the below. We can see first this is the apply ID 10010. Then is the full name of my at the last is the language just output the other language or Chinese. Another case of this extension method is PLPG-SQL query language, developed by PostgreSQL in PLPG-SQL, XML type, and The two JSON types are supported, JSON and JSON-B. A set of functions and function-like expressions are available for producing XML content from SQL data, such as the XML phrase shown here in red. PostgreSQL offers two types for storing in JSON and data, JSON and JSON-B. They accept almost identically set of values as input. The major practical differences is in efficiency. Although JSON data can also be stored as text, but the JSON data types have the advantages of enforcing that each stored value is valid according to the JSON rulers. There are also assorted JSON-specific functions and operators available for data stored in these data types. Diversified operators are the most obvious feature that distinguish PLPG SQL from other query languages. We can use the insert into and select clauses to insert document data, or use select clauses and matching operators or set functions to update document data. Next is the query operation for XML data. PLPG SQL's specific functions, XParse and XParse exist using XParse language to query XML documents. PostgreSQL also provides XPath-only variants of standard functions. XML exist and XML table, which formerly use query languages. For all these functions, Postgre only provided XPath 1.0 version. And for JSON data, query could use select clauses to query JSON data. Similarly to other basic types, returns a set of JSON data. Postgre circle provides two operators for querying JSON data by default. The operator the first operator returns JSON data object according to the key. And the next operator returns JSON data object according to the text. The difference is they return result by key or text. There are many other multiple model databases and multimodal query languages that use this method to extend the standard circle language and relational databases for example, the Teradata and the Teradata circle and Oracle and PL SQL circle. More detailed details can be obtained from their usage documents. Next, we will turn to the second kind of circle-based multimodal query languages, which supports a graph model. Now we enter the third part of this section. SQL-based extensions to graph store also not as prosperous as document support extension. Graph support extensions also occupy a considerable proportion of circle-based multimodal query language. The way that circle-based query language supports graph data model is related to the various classical graph query language styles. Generally, Graph model means property graph and RDF tuple. Roughly speaking, RDF is a kind of edge-labeled graph. Edges are labeled with relationships. Nodes can be literally or black nodes. A typical query language is Sparkle. In the property graph, however, nodes and edges are both associated with properties. The typical query language is a cipher. Therefore, this gives the birth to two typically circle-based graph extension language. Support cipher style and Sparkle style. It is worth noting that Oracle adopts different graph query styles to support them. For most circle-based query language that support a graph model, they adopt the same graph query style. That means, to some extent, Oracle supports the graph model more perfectly. Besides, we are glad to see some new explorations in this field. On SIGMOD 2020, DB2 published their IBM DB2 graph, which is in an database management system graph query approach to support collaboratively and traceable graph query in IBM DB2 relational databases. It is implemented as a layer inside DB2, and this can support integrated graph and circle analytic efficiently. DB2 graph employs a novel graph overlay approach to expose a graph view of the relational data. This approach flexibly retrofits the graph queries to extending graph data stored in relational table without expensive data transfer or transformation from the presentive or query language. IBM DB2 graph transforms and optimizes the Gremlin inquiry into circle statement. At last, MariaDB's query language called Open Query Graph extended the graph models by adding in graph-related functions in circle. This is also a very effective method. The case we present here comes from a new and growing in database natural space. The query language it used called graph circle. The to process graph data, specialized structure represent graph edges, graph nodes as records in relational tables. Foreign key to primary key relations are automatically visible as graph edges. Intermediate tables for many-to-many relationships are also visible as graph edges. A spatial structure representing graph edges specifically accelerates the graph queries processing as well as circle join queries that use foreign key to primary key relationships and intermediate tables. Graph circle is simple extension to SQL. It adds a new match expression. Match expression is a pattern describing what objects and relations we need to perform the query. Match replaces the formed clauses in circle. The remaining clauses select where, order by, group by, having into are regular circle expressions. Therefore, as long as graph can be represented as relational data, circle can also be used for simple queries on graph data. But graph circle is more efficient. We can see the example showing in the page. This is a graph data in which this is a friend relationship between people and the owner's relationship between people and cars. We hope to find all people who have cars and those who have friends and cars of the same model. We can see from the page that graph circle is more efficient. Here comes to the last part of this section, circle-based extension to another store. Some circle-based multimodal query language also support time series data models or geospatial data models. Of course, there are many in databases and database query language developers are trying to integrate machine learning approaches into Circle, make data analysis more convenient. There is not so much time. I will briefly introduce how MonetDB Circle to implement operation on geospatial database. Before using it, you need to reboot MonetDB and activate it when the server starts from the first time. GIS functions are packaged as a single Monet module. GIS module supports all objects and functions specified in OCG, simple features for Circle specifications. MonetDB uses 16 geometric data types in Circle, of which 11 can be instantial. Here is an example. We insert a building and then query. These are some references for these sections. And in the next, I will pass the stage to Qinsong. Thank you for your attention and watching.
Hi, everyone. Nice to meet you. I'm Qinsong, a postdoc from the Unified Database Management System Group, University of Helsinki. I will lead the discussion of the following three sections in our tutorial. Let's get started. We will take about 15 minutes to talk about the document-based multimodal query languages. Let's get started. For the document data, such as the XML and the JSON, they are self-describing by associated semantic tags or markers and enforce hierarchy of records and fields by listing elements within the data. They also enable more flexible processing and the exchange of data. Comparing to the traditional data model, they have rich typers. They could be schemaless and schemaless optional. For example, XML and JSON can be viewed as a laboratory if you consider about the ID and ID reference. So therefore, the XML turns to a schemaless label graph. And the document data also allow a scalable listed and the same structure format. So they are widely used in many application scenarios. In general, the document data can be thought of as extension and the restriction move of the relation model by supporting complex types such as arrays, list tuples, maps, and by removing the regular schema. Take JSON as an example. It supports two types of values. The first one is the primitive value, such as a string looks like hello, a number, or a Boolean value, true or false, and the null value. It also could be a structured value, such as an object and array. Objects are a list of name value pairs. Here is an example about the object describes some information about the part number about part number. For array, here is it is an only list of items. Here we have example of an array containing 5 items. The former 2 are numbers. The second is a string. The third one is a Boolean value, and the last one is the non-value. The adding an array and the value in the field of an object can be any JSON values, arrays, and objects. Typically, there are two types of document query. The first one is pass query. The second one is trigger query. Actually, trigger query is special of graph pattern. We'll discuss later. For the pass query, it is specify a pass from vertex X to end vertex Y. Regular pass query is a very important pass query, and by applying conjunction on the regular pass, several regular pass query, we can get conjunctive regular pass query, and if we replace the regular expression with context-free grammar, therefore we got the context-free pass query. With the regular pass query, we can specify the friend-of-friend relationship in a social network. Suppose we have several regular pass queries. By applying the conjunction, we can get a conjunctive regular pass query, and the XPath includes several 5 essential features. The first is learn test, including the name test and the node tag. Second is access, such as say ancestor or self, attribute, child, distant or self, parent, self, and so on. The third one is a relative navigation from starting from a context node. The fourth one is constant, such as numbers and literals, and the last one is operation, such as additive, multiplicative, and or equality, relational, unions, sign, and so on. Typically, we will represent XML document in document object model. It is a tree representation of XML data. Therefore, with the XPath query, we can navigate along the tree representation of the data. The X query including 2 essential parts. The first one is a flower expression for late, where, or by return, and second is XPath expression. A flower expression supports iteration and banding of variables to intermediate result. This kind of expression is often useful for computing joins between 2 or more documents and for restructuring data. Here example, XML file about the breakfast menu in a collection of menu. It describes some of the breakfast food information about the breakfast food. It will be used later. So here's in order to use the XPath as query to extract subset of data, we can just apply the path expression and flower expression. Here are 2 examples. In the first example, we want to get the name element from each food whose price is less than $6. So we can combine the access and the node test in here. The axis is chat axis by specifying the sub element in the element, such as a breakfast menu from the connection and sub element of food and the sub element names from the food with the price sub element price less than $6. The second, the query. We will go through all of the documents in the collection, and for any breakfast menu, get the name of food with the price less than $6. So at first, in the forecast, we will retrieve every document in the collection from the collection. Thereafter, in the where class, we use expressive pressure to filter out all of the food with price less than $6, and then return the name of the food meet their condition. Right. Right now we'll use modular logic as example to exemplify how is XML XPath and XQuery can be extended to support multimodal data. MarkLogic is a document that DBMS extended to support multimodal data such as XML, RDF, JSON, full text search. It allowed to embed the RDF triples in XML documents. Below is an example of embedding two triples into XML files. The first is John Smith lives in London. Now the second is about the John Smith lives in Helsinki. Right. In this way, we can embed the RDF triples into our XML document, and MarkLogic extend XQuery with Spark syntax to retrieve RDF triples. For example, if we want to know which person lived in Helsinki, so we can issue the following query. We just need to select the person name where the person lived in Helsinki. So if we it's a little bit different from the JSON document because we can't embed the JSON document into XML files. So we need another way to handle the JSON document. Actually, similar with the with XML document, JSON will be first passed into a DOM tree, and thereafter we can navigate the JSON tree representation of the JSON file with XPath query. Here is the example. It's a very simple JSON document, but with some of the records. Yeah. After transfer it to a DOM tree, the root is a DOM node, and thereafter is a document is an object node with a with name with no name, and its value is value including 4 nodes named A, B, C, D, and A is a text node, B is a number node, C is an object, is also an object, and D is a non node. Node C has 2 records. The first 2 records F and G. F is a Boolean. It's a Boolean node, and G is a read node, right? G includes three subnode called called V1, 2, and 2. So therefore, in this way, we can transfer the JSON into a tree representation similar with the XML. And with XPath query, we can navigate the tree and got the result with what we wanted. And here's in this table we have several examples of navigating the DOM tree. In the first 9, we're going to navigate from the document, from the root node to node A. So we will get text node, and its value is value. Okay. In the second 9, we navigate from the XPath in this XPath expression. We navigate from the root node to a number node with named B, and the return result is the number node with value 10. So if we want to know the value of this number node, so we just add a data function, so therefore we can get the value of extract the value from the number node. Similarly, we can navigate to any other node in the. Actually, it is impossible for logic to integrate relation tables into its data model, but provide ways for binding relation data with XML documents. It means that there is no way to retrieve a relation data with XPath or XQuery expressions. But logic also provide an alternative way by extending XQuery with function for manipulating relation tables. It provides 2 functions named generate table fetch and execute SQL. Normally, document data are viewed as a special case of graph data. So the XPath and XQuery provide basic support for navigation and pattern matching of the graph data. But unfortunately, they don't support the regular path query and the conjecture regular path query. But the core XPath syntax can be easily extended to support the regular path query of graph data by adding 2 operators. The first is transitive closure operator, and second is subtree relativization operator. But it involves a lot of theoretic proof, so we will not discuss the details here. In general, the existing core language, such as XPath and XQuery, can be laterally extended to support JSON document and graph data, but they can provide good support for other data types, such as the relation data and RDF triplets. In the next section, we will take about 25 minutes to discuss about the graph-based multimodal core languages. The graph data model is normally viewed as a generalization of the relation model and semi-structured model. It consists of a vertex set and the edge set. Typically, there are 2 types of graph data models. First one is the edge labeled graph, where edges are labeled with relations. Node can be any unified resource identifiers, literal or blank nodes. The second type is a property graph, where node edges are labeled and each associated with a set of properties. For the edge label graph, each edge has a label to indicate the type of relationship described in the domain. Edges are directed, and it is widely used for gaining knowledge about semantics, which form the basis of the RDF data model. Here is an example, including three RDF trippers, saying John is a student of University of Helsinki. Bob also is a staff of University of Helsinki, and Bob teaches John. So the three RDF trippers forms our age-labeled graph. For the property graph model, node has labels, node has key value properties, relationship have labels, and the relationship have the key value properties. All of the relationship are directed, and the semantics of the direction is up to the application, right? And here is an example about the product customer graph. In the graph, there are three nodes. Two of them are customer node. For example, the node with ID 1 and the node with ID 2 are customer node, and the third node is product node, and there are relationship between the nodes. For example, the customer 1 bought the product with ID 3 and February 1st, 2021, yeah, and price $100 with 5% discount. And similarly, the customer 2 have also bought the product and January 1st, 2021, and price $120 with discounts of 5% discounts. So, and also the customer follows customer 1 follows customer 2 since the October 1st, 2010, and the customer 2 followed by since October 2nd, 2010. So there are 4 kinds of typical graph pattern graph queries. The first is graph pattern matching. It is conjunctive query over the relation presentation of the graph. For example, someone has won Nobel Prize, someone has won Booker Prize, forms a very simple graph pattern, right? The second is path query for navigating along connecting edges. In this example, actually, it is a regular path query, asking for a person who is a citizen or of a place Y, or born in or lives in place Y, and located in place Y for several time periods, right? And the third tab is the variable for manipulating data found during the navigation. And the last one is aggregation. In this tutorial, we only focus on the former 2 types of graph query. Actually, the graph pattern and the graph query can be laterally combined to form more complex graph query, such as conjunctive regular path query. So in this example, we combine the former 2 graph queries for asking someone has won Nobel Prize and also won Booker Prize, and he lived in some place Y, and he is a citizen of place Y, or born in or lived in place Y, and thereafter he located in place Y for some time period, right? The regular path query is very important graph query. It has form of triples X, R, Y, where R is the regular expression of the vocabulary of age labels, right? The construction of the regular explorer follow the following rules. The first R could be a simple element from the vocabulary of Edge labs. It could also be the composite of two regular expressions, and it could be a disjunction of two regular expressions, or it could be an encore of regular expressions, right? And it also could be of R question. It means that 0 or 1 occurrence of R, or R star. It means that 0 or more occurrence of R, and R plus means 1 or more occurrence of R. Yeah, here are two examples about the regular path query, and system relationship is equivalent to the child of plus, and the cousin is a conjecture of four relations. Is child of and has child of. Okay, let's look at an example about regular path query. Yes, in this regular path query, start from label A plus, and then followed by D or C, and then followed by B and E. So in this graph, there are two matched results: ACBE and AACBE. For the ACBE, we start from the vertex 2 to 4, 4 to 5, 5 to 7, 7 to 9. Right. For the second, we start from the vertex 1 to then go to the vertex 2 and 2 to 4, 4 to 5, 5, 7, 7, 9. Here we have a triangle pattern. Right. Triangle pattern with three edges, and the edge between x, y labeled with A, and the edge between y, z labeled with E. The edge it doesn't matter of the label for the edge between z to x. So there is 0, 1 match triangle in this graph. From this graph, it's 7 to 8, 8 to 5, 5 to 7. Okay, we can, as we said, we can combine the regular path query and the pattern query, right? So here we have a conjecture regular path query, and actually it is asking for a cycle where for the edge between x y labeled with A, and the edge between y the edge from y to z labeled with E, and there is a path from vertex z to vertex x following a regular path, right? Question C plus and followed by D or B, right? So there are three cycles measure the conjecture regular path query. So the first one is 7 to 8, 8 to 5, 5 to 7. So the second is 7 to 8, 8 to 5, 5 to 4, 4 to 7. And the last one is 7 to 8, 8 to 5, 5 to 4, 4 to 6, 6 to 7. Okay. In the next, we will exemplify, we'll use the Spark and the Cipher to exemplify how the graph-based current language can be extended to support multimodal data, right? For the Spark, it is a current language of semantic web. working on RDF graphs of SPO triples, and the results are represented with unified resource identifiers. Objects can be literals, strings, integers, Boolean, and so on. The Spark query consists of two parts. The first part is about the prefix declaration. The second part, the from clause specifies the dataset, and selection. The select clause specifies the result, and the where clause specifies the query pattern, and the order by defines the query modifier. Here is example of asking for all the people in Team Berenice friend of friend file that have names and email addresses. So in the prefix, we declare the friend of friend, right? And in the select, we want to know the name and email of from the friend of friend files, and from a dataset, specify the URL. So in the where clause, we are looking for some person with name, with specified name, and this person also with a specified mailbox, and finally we order by the name of the person. Okay. Here, sorry about the of using the Spark query to express the conjecture regular path query. Right. We will take the product customer graph and conjecture regular path query. The product customer graph have two vertex tabs, product and customer. Age also have two types of age. The C bought, customer bought a product P, and customer follows product follows another customer. And the query is asking for a person, a friend of friend of two customers who bought toys in common. Yeah, in the query, it consists of two regular paths. The first one is C follows plus C1, and the C follows plus C2, and the C1 brought product P, and the C2 also brought product P, and P was category toys, and C1 is not equal to C2 because you are looking for different customers, right? Express this conjecture regular path query with the Spark syntax. It could be like this. So at first we select the three customers, C, C1, and C2, where in the where the conditions there are also two regular path query. The first is C follows at least one times of customer C1, and the C follows also at least one times of C2. Actually, the follows plus means that the traversal depth is at least one, right? You traverse the graph, traverse the edge, labeled with graph occurred at least one. Okay. So, and the C1 bought product P, and the C2 also bought product P, and the P has category of cat, and after we have to we have a filter statement that the cat equals to toy and the C1 smaller than C2, and finally we group by the customer C1 and C2. Actually, the Spark can be extended in 3 ways to support other kinds of data types. At first, it can support SQL procedure and aggregations to support relation data, and it can also extend with the keyword search over RDF data to support key value data. Yeah, and the third one is extend Spark with flower expressions to support XML data. In this example, we show how to extend the Spark with defined SQL procedure, right? Here, here we embed a SQL procedure compose information into this selected clause, okay? And from a data set where we are looking for someone has type of person, and someone has a specified name, as have a legal name. The person have a mailbox. Okay, and as we said, we can also extend the Spark with SQL aggregations. In following example, we're asking for which city is in the UK has the largest number of university, right? And we have to select a city and count the number. Where there are 2 patterns. The first is a university of United Kingdom, located in the United Kingdom, and the second is specifying the university in a city, such as the London. So we can group by the university and city, and in a descending order, right? So the first output the city and count pair tells us the the city with the largest number of university in UK. As we said, the Spark also can extend to support full text search by building functions contained, right? So it's quite simple. We just skip it. To support expert data, so the Spark can be extended with XQuery syntax. So we call it as XSpark. It just extends the flower expression, right, for manipulating the XML data, and it also have extend the constructor and the return keywords to support constructor of XML files and return XML files. Okay, here in this example, we are following the instruction to extend the Spark with the XQuery syntax, right? And first, we declare 2 namespace, friend of friend and an element namespace, right? And here we have a temporary variable doc. It is assigned with a designated document, and then we let friend equals to any elements which is a distance of the document node, and it has an attribute ID equals to foreign, and it also has a sub element span. It has a attribute class equals to V card. So thereafter we see we can extract the information from the document and to construct the result from as we need it, right? So for each friend in the friends, and let the friends account equals to equals to the hyperreference to which is a sub element, which is a distance of the FF. So, and thereafter we can construct our XML document. No, it's an XML element. Then, and then we can return it to the user. For the cipher, it is widely used Korean language developed by the Neo4j. It assumes a data model of labeled polygraph followed by non-repeated age isomorphism semantics. Its basic cipher syntax is like this. It consists of 3 parts. First is match clause, match for nodes and relationship of interest. In the where clause, we are doing the filtering with labels and the properties, and then we will return elements to retrieval. Again, we will use the product customer graph and the conjectural regular path query example to show whether cipher is capable of expressing the conjectural regular path query or not. So actually, it can. In the cipher conjectural regular path query, in the match clause, there are two patterns. There are 2 patterns. The first one is for the custom C. It follows by custom 1. It also follows by custom C2, right? So and we have a product P. It bought by the custom C1, and it also bought by the custom C C2. It means that it is the product bought by two customers in common, right? So, and first pattern is the customer follows by follows both by 2 customers, C1 and C2. Okay. In the word class, we specify the filtering. Is P dot category is 2, and the C1's name is smaller than C2's name, and thereafter we return C1 and C2. Similarly, the cipher can extend it in multiple ways. In the first, it can extend the seeker syntax to support the relation data, and it also can extend with the user-defined function or procedure to support a machine learning model. And here is the syntax of extended cipher with seeker queries. Actually, in the word class, you can extend the variable to the filtering condition to support the columns, and you also implement operators that can make comparison between the the variables of the traditional cipher and with the value from query result from the seeker query, right? So similarly for the return, you have to support 2 kinds of data types, column or regular cipher expression, right? So below is an example, right? As we said it before, in our Unibench example, right? Information are keeping keeping different type of models, right? And for the friendship about customers, are keeping a friend graph, and the customer information are keeping the customer relation table, right? So if you want to find all of the friends of a customer whose credit limits is over 3,000, so at first you can match the friend of a customer, and in the web cross you select the friend from the friend graph, and if it equal, and also you have to select all of the customer with credit limits over 3,000, and make a comparison between this result, and if their friend ID equals to the customer ID, it means that you got the result right. So, and second, we can also extend the cipher with regression models. In the following example, we are using a regression model to predicate the price of room on Airbnb with the historic price of neighborhood rooms. And in the match cross, we're adding all of the neighborhood to a list of ID of the label with ID 78704, and the word cross specify if the list has better rooms, or if the list has price and the list have not been trained. So we can call linear regression model to add all of the neighborhood prices and the bedrooms, and then train it. After the training, we can use the linear regression model to make prediction about the bedroom list, right? So in general, the existing graph-based model query languages support regular path query, and also support complex regular path query, but they are very hard to use. Section, we will take about 15 minutes to discuss about native multimodal query languages. The most important feature for a native multimodal query language is cross-modal query, and is that one unified query language can manipulate multiple data model in a single query. There are two native multimodal query languages. One is ArrangDB query language, AQL, and ArrangDB query language, OQL. ArrangDB support graph key value JSON, and it can do queries with AQL for retrieving data, with filtering, sorting, and more, and traversing through a graph with different options. It also can handle shortly path query, graph pattern matching, and also cross-model query. And first, we'll give you some basic examples to show how we can use AQL to traverse graph. And first example, we are going to selecting all rows documents from a table or collection with all columns and attributes. Yeah, in second example, we are going to be filtering our documents from a table collection with projection. And in the last one, we are going to sorting rows documents from a table or a collection. And AQL has its own implementation of drawings coming from SQL background, but the AQL syntax is very different from SQL. Inner drawing can be expressed easily in AQL, listing for loops and using filter statement. And in this example, there are 4 loops. In the first loop, we're going to take all of the user, and in the second loop, for each friend in the friends collection. So we're doing the filtering. The condition is friend's ID is equals to user's ID. Then we can return the result by merge the user and friend. Our join are not directly supported in AQL, about can be implemented using a subquery. We're not going into the details about the query. The AQL also I can also do the graph traversal. The syntax including 5 classes. The first 9 is a for class. It works on vertex, edge, or path. And in the second 9, specifies the minimal and maximum traversal depths. And the third 9 specifies the traversal direction, outbound, inbound, or any from our starting vertex. And the traversal can work on a graph or edge collections. And finally, we are doing some pruning. And this for loop doesn't iterate over a collection or an array. It works the graph and iterate over the connected vertex and fence with the vertex document assigned to a variable. Here we have a collection of flights from one airport to another airport. In this example, we have a flight. ID is 7613 from the Peking International Airport to Pudong International Airport. With AQL, we can traverse to the parents of the Peking International Airport with the following query, and they in the in clause there's traverse depths because we just want traverse to the parents, so the traverse depth is 1 to 1, and direction is outbound, so as we can traverse to the parents, and with this query we can find all of the parents of the Beijing International Airport. Similarly, we can traverse to the children, just modify the traverse direction to inbound. And also we can traverse to grandchildren or grandparents. But with alteration of on the traverse steps to 2, and the direction in as the inbound, right? So therefore we can traverse to the grandchildren. And also we can traverse with variable depths. Here we can traverse from the Beijing airport, the Beijing International Airport, up to the to another airport with traversal depths from 1 to 2. It means that we will search for at least 2 edges, right? So in this way, we can find all of the direct flights to from Beijing, or indirect flights from Beijing with at the most 1 transport airport. So with the traverse with variable, we can implement the breadth first search and depth first search. And also the AQL implemented with many graph algorithms such as the shortly path search. So it is very powerful for graph traversal. And AQL also supports simple graph pattern by leveraging join to express the graph pattern. But there's no way to express. There's no easy way to express the graph pattern. Here is an example, a diamond pattern. Yeah, we need four loops to do in the join. Yeah, in the first for loop, we're specifying the edge connecting from S to A, and second, we're looking for the edge from A to C. The third for loop is checking for the edge connecting B to C, and the last loop is checking for S to the edge S from S to B, right? So it's very complex to express this kind of very simple pattern, and because AQL does support recursive traversal, so the regular path query and the conjecture regular path query can be expressed with AQL, unfortunately. Next, here is an example about a cross-model in the Unibench use case. We have information stored in different types of data models. The information about customer are stored in a relation table, customers, and the friend relationship between the customer are kept in the friend graph, and the order information are kept in our order documents, and the order made by the customers are kept as key value pairs in a key values store. So if you want to retrieve data from all of these different types of data model, you have joined the corresponding data together. Okay, issue the following AQL query. Yeah, because in the query we have to retrieve data from all different types of data models, right? So, and the information, the corresponding information are kept in different type of data. And for example, the customer information are kept in the customer relation table. And so we'll let CID a temporary variable to keep all of the customer with the credit limits over 3,000, right? And yeah, because the friendship are kept in the friend graph, so we use our temporary variable FIDs to keep all of the friend by retrieving from the friends graph. So, and thereafter we use two full loops to join then the temporary variable together, and yeah, for each friends in and for each order, we are doing a filter by comparing the order number equals to the custom from the order in the custom to order. If they're equal, then we can return the product number and the product name from the order names. Next, we'll discuss about the ORAN-DB's core language. ORAN-DB supports documents, graph, spatial, and full text, and it extends the SQL language, and the vertex and edges in RNDB are JSON documents. There could be schemaless or schema4 or schema hybrid, and there can be less documents, and they have rich indexing and query. And the OQR borrow the syntax of seeker. So we're having selector, we're having from, we're having group by class, we even have having class, right? So about, as we said it, the OQRs also support graph. So we need traversal and match to extend the SQL syntax for supporting the graph traversal and graph head matching, right? But the traversal keyword is deprecated. And the RNDB also implement some very useful graph functions to represent the connection between two nodes, such as R, in, RTE, and in E, H. Here is an example of showing that using OKR to do graph traversal. Yeah, for example, going to experiments from starting vertex. So you just expand an out function or expand in function from the flights connection, where the key equals to some airports, right? So here key is the Pudong International Airport. So the result would be Peking International Airport and Helsinki Airport. So if you want to get all of the outgoing and incoming vertex connected with edge with neighbors from all flights around the world, so you just specify a condition in the out or in condition here, or the condition is Pudong International Airport. So you can find all of the outgoing and ingoing airport from the Pudong International airports. By combining the by combining some of the graph functions, we can do more with the graph traverser. Here is example of combining two out function. So, and therefore we can traverse with two steps out, right? Therefore, the result is Helsinki Airport, and similarly, we can expand two in functions from the Helsinki Airport. So the result will be Peking International Airport. Okay, the syntax for the graph pattern matching, including four clauses. The first is match clause, including the edge pattern and connecting with the function name. And after we can specify the conditions, some of the conditions for on the function, such as where condition, why condition, and max steps condition. So, and then we can return the result, and followed by the group expression and order expression, order by expression. And here is an example of pattern matching. We're looking for the indirect flights from the Peking International Airport to the Helsinki airport. So with one transfer airport, so we can combine two out functions, and like this. as we discussed before, the diamond pattern also can be written in OQL, right? But in the match class here, in the match class, we have 4 edge pattern. The first edge pattern is about is going out from S to 8. The second is going out from A to C, and the third one is is to find the edge from B to C, and the last edge pattern is from S to B, right? So by combining the edge patterns, so we can get a fully connected diamond pattern. Okay. Unfortunately, OQL also doesn't support recursive traversal, right? So it's impossible to support the regular path query and the conjunctive regular path query. And similarly, we can implement the cross-model query we discussed before with the OQL, right? But it is different from the syntax we use in the AQL, right? So here we also need 3 table variable to keep the intermediate result, such as the customer with credit limits over the 3,000, and table variable CID for keeping all of the friends of our customer, and table variable code for keeping the custom to order information right. And in the where class, we are doing a join. Therefore, we can get out of the result. So let's make a summary. The existing native core language supports basic graph traversal and graph pattern.
Hi, this is Charles here. In the next, I will demonstrate 2 multimodal query languages, the ArangoDB query language, or AQL, and the OrangeDB query language, or OQL. We will use the data and queries from Unibench, which is a benchmark for multimodal databases developed by our group, and all the materials in this demonstration have been released at the GitLab repository here. So now we get started. And this repository contains all the data, importers, and the query implementations. And you may try yourself after the tutorials. And we first demonstrate the AQL by ArangoDB. So to better follow this hands-on session, please install the ArangoDB in advance. And in this demonstration, we use the community build version 3.4 of ArangoDB. And we will use the ArangoDB web URL to perform the queries. And the default URL is here with localhost porter 8529. So the first supported data model is the document model, which are organized as collection and document. And we all know that the relational database contains tables or records. And in an ArangoDB document database, it contains the collection that including a number of documents. And these documents follow the JSON format. So below here is an example of a score JSON document with the ID, name, and an array of scores with the 3 elements. So the very first step is to import the file to the server by using the Argo import utility. So here we first import the scores collection. Now in the web interface, here we can see the scores collection has been created, and it contains a set of rows, and each row here is a document, has a JSON document here. Okay. And now we try some queries for the document. The very first query is to return a score document in the collection. Under the queries tab, now we can try run this query here. So the AQL uses a for-in filter syntax to return the document. Here we can see there are two documents and rows have been returned, and these documents have a same name with Leonida. So to further filter this document, we can add additional predict in the filter clause. Here we can further filter this document with additional predictor. And we can also use AQL to access the array with a wildcast operator. So for example, we can directly return types in an array. Here we see types are exam, quiz, and homework. We can also do a inline operation in the array. Here we add another filter in the array to return this score more than 90. Okay. And then we can also do every aggregation on this array. And when dealing with the nested array, we can use the flatten keyword to flatten the array. And we can do twice to get a flattened array. And in AQL, you can use the sort in the array to sort these documents. Here we sort the first element of the scores. That means we sort the documents by the exam score here. And also we can group this score by name. And the AQL uses connect into syntax to group the documents. And we can also use a with count syntax to further count these documents by name. Here we can see some documents have the same name. And AQL also support using the let to define a variable here we use let to define the average score for each document and then sort them in a descending order here. And finally, for the documents, the AQL supported the nested loop join between the documents. Here we join these two collections. We do a self-join on the document's name. All right. So in addition to the document store, the AringoDB also supports the graph store. And a graph database in AringoDB contains a set of node collections and age collection. So in the next, we show how do we deal with the graph. We use a built-in graph called nodes graph in AringoDB. And now we can see the collection contains age collection and a vertex collection. So to traverse the graphs, the AQL follows the following syntax. So it can traverse the vertices, edges, path for a graph with a start vertex in either outbound or inbound or any directions for the graph. So we can now first find the friend for a given person. So we first get a random person P, and then we find their friends. Here we define the path is 1, and we return all the friends and ages of the given persons here. And an interesting feature of the AringoDB is that it can return the results as either a graph here or a JSON document. So we can also do some filtering over the graph. We can do a filter on the vertices, of course. Here we filter the friends whose name is Alice for Rob, for Bob. You can also do a filtering over the paths. Here we restrict the length must be more than 1. So here we find 2 persons with length more than 2 for Bob. And we can, AQL also supports some graph function, such as the shortest path. Here we would like to find the shortest path between the Charlie and Alice. Here we get a shortest path between Charlie and Alice with an intermediate node called Bob. And a salient feature of AQL is that it supports querying the multimodal data sets. And here we use a simplified data set from Unibench, including 3 files: the nodes graph, the order JSON, and the person table. And first of all, we import this data into AringoDB. All right. So now we have successfully imported the 3 files into AngularDB. And there are 5 tasks for querying the multimodal data. So for example, the query 1 is to get the top 10 best-selling products in all orders. So first of all, we find the product from the order, and since they are nested row, we need to use a flatten to get the product list, and then we group by this list by their product ID and count them. Okay, now we get the top 10 with the maximum count for product ID 4244, 3,700. And the second query is to calculate the total cost of the females orders in year 2008. So this query will involve cross-model join between the person's table and the JSON order. So here we do the join in the filter clause and specify the 2 additional predict between the person and order, and then we sum the total price. Okay, so the total price for the females order in year 2008 as follows. And the third query is to return the number of orders made by the person's friends. So here, this query is a multimodal query involving the graph and JSON order. So here we do a join in the filter clause between the graph and the JSON with the start vertices, and then we count them by keys. Here we can see this cross-model join is expensive than the previous queries. And the AQL supports the explain features to see the execution plan. For example, here we can see the estimation cost for each node are listed as follows. And here we can see the enumerate the connection node has a high estimated cost. Okay. And the fourth query is to find the shortest path between 2 given persons. And then the query asks the top 5 best-selling products for all persons in the shortest path. And so the first step is to return the shortest path between these 2 persons. And then we do a join between the intermediate results with the orders, and then flatten this product list. And finally, we group these products by the product ID. Okay, so the third query has been successfully executed, and the result is 5,082. Okay, so the top 5 best-selling products in the shortest path are given as follows. And finally, the query 5 is to find the top 10 persons who spend the highest amount of money in orders. Then we do a graph traversal for each person with 3 hope friends, and return the number of common friends for these 2 persons. So the first step is to find the top 2 persons by using a group by on the order's total price, and then we find the 3 hope ratio and for each person separately, and then we use an intersection function to find the common friends between these 2 sets. Okay, so finally we get the number of the common friends between these 2 persons are 2,069. Hello. In the following, we demonstrate the OrangeDB query language. We use the community-built version 2.2.35 of OrangeDB to demonstrate the query. So the OrangeDB engine supports graph, document, key value, and object models. In particular, OrangeDB uses the concept of classes and cluster as its form of convention for grouping documents. And a class can support multiple clusters. And similarly, we query the score documents in ArangoDB. And in particular, we import the file to the server using its ETL2 OETL. And with a configuration file. So an example of configuration for the score document is as follows. And we need to specify the source, the extractor, the transformer, and the loader. So in particular, for this case, we transform each line in the JSON file to a JSON document. So the OrangeDB use a SQL-like path-oriented query language and some extension to the graph. So firstly, to return a score document in the connection, we use a very SQL-like query select from where with a specified name to find the documents. And we can further add a specified ID of the documents to get an exact result. And we use a dot operation to access the array, and to further filter the nested array, we must unwind the nested scores and then specify the filters in the while clause. And similar to SQL, we use a group by, order by clause to do some aggregation over the data. But in the nested SQL, here we must unwind the nested scores. And the OrangeDB graph database contains a set of vertices and edges. And a vertex is an entity linked with other vertices, and the edge as an entity that links two vertices. So in the following, we use the built-in grateful data console graph in OrangeDB to show some graph query examples. So by looking at the schema manager here, we can see the OrangeDB supports the schema mixed mode for the query, that the vertex can be an artist or can be a song, and these entities or vertices are linked by the edges. So first we find the writer of a given song named repo here. So here the results are returned, and we use a path-oriented operation to return the authors. And we can further find that these authors same song with another dot operation. And furthermore, OrangeDB has implemented a dedicated command for graph traversal, the traverse keyword. So to get the writer of a given song named repo and find the song he sang, here we use the traverse syntax to find the related entity. And particularly here, we specify the max depth of this traversal as 3, and we use a breadth-first strategy to traverse the graph. And the OrangeDB also supports the shortest path function, and by declaring two variables from 2, and then return the results as paths. Now we get the shortest path between the hunter and the grassy. And the OrangeDB also supports querying the multimodal data sets. And in particular here, since we have to create links between the persons and others, as the join operation are not supported in OrangeDB. So here we create a link between the person's ID to the other's person ID. Now we are ready to query the multimodal data. So the very first query is to return top 10 best-selling products in all orders. Here we use unwind operation to flatten all the nested order lines, and then we use a group by function to group these products, and then we get the top 10 products. And the second query is to find the total price of the females orders. So similarly, we use a nested SQL query to find the related data. And for giving a star person to return the number of orders by the friend's friend, we can simply use a path-oriented operation to return these orders of friends. And to find the best-selling products in the shortest path, we first embed a SQL with the shortest path function, and then we use a path-oriented operation to find the related products, and then we do the group by operation. So here, top 5 products are returned. And in fact, finally, we use a similar way to find the top 10 persons from the orders. Then we do the graph traversal for each person with maximum depth 3, and then we return their common sets of friends. Okay, then the final answer is return. Thank you for your attention. In the following, we will discuss the open challenges and the future directions for multimodal query languages. We discussed them from 2 aspects. The first one is to design an algebra for a multimodal query language. And the second aspect is to develop a general approach for multimodal query optimization. Firstly, we know that the SQL has the relational algebra, and the XQuery has XML algebra, and the SparkQL has a graph algebra. So now it calls for a unified algebra for multimodal query languages. We think there are 2 promising directions: the category theory and the associated array. Basically, the category theory formalizes the mathematical structure and its concept in terms of label-directed graph called a category, whose nodes are called objects and whose label-directed edges are called morphism. And the associated array, also called maps or dictionary, are an abstract data type that can hold data in key-value pairs. And there are 3 directions for multimodal query optimization. The first promising direction is to provide a unified framework for the cross-modal query optimization, which is cost-based. So we have studied the problem of relation tree joint selectivity estimation at ISSDVM 2020. So now the next step is to study a more complicated case that involves the relation tree graph simultaneously. The second promising direction is the view-based query processing. So we have developed a graph view selection tool called GRView for relational databases. And the The next step is to consider the hybrid view selection for multimodal databases. So the motivation is that a multimodal query may involve operators from various data types, data models, or for instance, when a query includes both the graph pattern matching and group by clause, in this case, we can combine the relational view and the graph view to accelerate the query together. And the third direction is the unified indexing techniques. So we all know that the B tree is for relational data, and now we need a unified indexing for multimodal data as well. Thanks for your attention. Now we are happy to take any questions. Thank you.